Now that we've seen or we're reminded of what polar coordinates are about, we're going to turn our attention to derivatives for equations in polar coordinates. dy dx is going to look a whole lot like what we saw with parametric equations. dy dx is equal to dy d theta divided by dx d theta. Considering r as a function of theta, when we see that x is equal to r times the cosine of theta and y is equal to r times the sine of theta, they become x is equal to f of theta times the cosine of theta, y is equal to f of theta times the sine of theta, where we see that f of theta is replacing r in our conversion equations between rectangular and polar coordinates. Using the product rule, dx d theta will then become dr d theta times the cosine of theta, so u prime v plus uv prime. In terms of r, that's going to be minus r times the sine of theta, the minus coming about because the derivative of the cosine function is negative sine of theta. So it's like f prime of theta and then f of theta for the u prime and the u for the product rule, but we're expressing it in terms of r instead. dy d theta is similar. We have dy d theta equals dr d theta times the sine of theta plus r times the cosine of theta. All of this leads to dy dx is equal to dr d theta times the sine of theta plus r times the cosine of theta divided by dr d theta times the cosine of theta minus r times the sine of theta. Let's note that at the pole, r is equal to 0, so these terms that have r in the numerator and denominator will be 0. dr d theta divides out. So dy dx is simply sine over cosine or tangent of theta, provided that dr d theta is itself not equal to 0. Otherwise, we'd have 0 over 0, right? A whole different thing. A polar graph will have horizontal tangents when dy d theta is equal to 0, provided dx d theta is not 0. And vertical tangents when dx d theta is equal to 0, again, provided that dy d theta is not also 0. We're now going to find a derivative and then use it. Find the slope of the tangent line to r equals 2 plus the sine of 3 theta at theta is equal to pi over 4. All right, so keeping in mind that x is equal to r times the cosine of theta and y is equal to r times the sine of theta, x becomes 2 plus the sine of 3 theta times the cosine of theta, and y becomes 2 plus the sine of 3 theta times the sine of theta, where we have 2 plus the sine of 3 theta playing the role of r in the conversion equations between rectangular and polar coordinates. Now, of course, in order to find the slope of the tangent line, we need dy dx. And we have this formula that we just saw involving the derivatives of y with respect to theta and x with respect to theta, but we don't need to memorize those. In fact, if you never do, it's okay. Because we have an expression at x that is a product. We can find dx d theta using the product rule. Likewise, dy d theta. And so I'd like for you to do just that. Find dy d theta and dx d theta, and then use dy dx to find the slope of the tangent line at theta equals pi over 4. Pause the video, come back when you're done. Well, I do hope you had fun. dy d theta is going to be 3 cosine of 3 theta times the sine of theta plus the quantity of 2 plus the sine of 3 theta times the cosine of theta. Substituting pi over 4 in place of theta is going to give us 3 pi over 4 everywhere we see a 3 theta, and pi over 4, of course, where we see theta. Since the cosine of 3 pi over 4 is negative 1 over the square root of 2, and the sine of pi over 4, the sine of 3 pi over 4, and the cosine of pi over 4 are all 1 over the square root of 2, we see those numbers showing up here. So we have negative 3 halves for the first term, and then for the second term, what I've done is used the fact that 2 is equal to the square root of 2 times the square root of 2. So 2 divided by the square root of 2 that we see here is the square root of 2 times the square root of 2 divided by 2. It turns out to be the square root of 2. And then negative 3 halves plus 1 half. We end up with dy d theta evaluated at theta equals pi over 4 is the square root of 2 minus 1. Similarly, dx d theta is equal to 3 times the cosine of 3 theta times the cosine of theta minus the quantity of 2 plus the sine of 3 theta times the sine of theta. Similar things happen with the 3 pi over 4 and the pi over 4. Cosine of 3 pi over 4 is the only one that has a negative value, and everything else has a positive. Don't forget, though, that there's a minus between the two terms. We end up with negative 3 halves minus the square root of 2 over, minus 2 over the square root of 2, minus 1 half. Same thing with this 2 over the square root of 2. We end up with negative 2 minus the square root of 2, if you will, for dy d theta evaluated at theta equals pi over 4. Putting these together, dy dx is going to have a numerator of 1 minus the square root of 2 because I'm applying the negatives from dx d theta, and a denominator of 2 plus the square root of 2. I hope that came out through all right for you. Notice that I didn't keep it in the structure of dy dx the whole time. It would have been a lot to write down, so I just computed dy d theta. Separately, I computed dx d theta, combined them as one fraction at the end. You could go either way.